GH2. That is the final expression of what Bernoulli's equation when you have. So do initial and do final. 1 and 2. So replicate it. Wherever you see V1 to V1 square, then GH1. 1 over 2 rho V2 square plus rho GH2. So that is what you have for the final expression of Bernoulli's equation. Alright. So, but if your pressure is moving in one direction, you know you have P1 here, pressure 1 here. If pressure 2 is coming to meet it, what's going to happen is that you're going to be having P1 minus P2. Okay, that's change in pressure. So you have rho V2 squared at the other side. So we can have is equivalent to 1 over 2 rho V2 squared minus, if this one is going to the other side, you change to minus 1 over 2 rho V1 squared now. Okay, then we have plus rho GH2 here plus rho GH2. Okay, then we have the final, which is GH1, that is minus rho GH1. Alright, so if that is what we have, then P1 minus P2 will give us change in pressure is equal to 1 over 2 rho V2 squared minus 1 over 2 rho V1 squared plus rho GH2 minus rho GH1. Okay, now in Bernoulli's equation, the heights of the object are the same, alright, and if you have a uniform area, alright, volume and velocity, volume are also the same. So you have rho is equal to, so you can use this expression when you have two different forms. Okay, but if you have uniform area or uniform volume, uniform area will actually suggest uniform volume, uniform area, uniform volume. So V is going to be the same. So what is going to be left if V are the same? If V are the same, all right, we can have 1 over 2 outside. Okay, or sorry, if it's uniform, if area is uniform, all right, V is equal to 0. So if V is equal to 0, so I can do 1 over 2. Alright, rho this V2 square. Rho is outside, then into. So I can say V2 square minus what? V1 square. Alright, then plus height is also the same. Alright, H is equal to what? H1 is equal to H2 is equal to H in Bernoulli's equation. Alright, as the case may be. Because sometimes they can give you one height, then you have to look for the other. But height are the same actually. So you have rho G will be outside, alright, then open bracket. What is left? H2 minus what? Minus H1. So change in pressure is equal to 1 over 2 rho multiplied by, I said for uniform cross-sectional area, V is equal to what? 0. So you now have what? 0 plus what? Rho GH into, I say H2 minus H1, alright, H is equal to the same, so it's equal to H. So you have what? Rho G. I did, right, so that is rho GH, okay? So rho GH, now you have changing, alright, rho is equal to this 0 plus rho G, because I said if your area is uniform, your V is equal to 0, so 0 plus rho G, so you have rho GH is equal to rho pressure, change in pressure is equal to rho GH at the final value. So that is that for Bernoulli's equation. Okay, then the other thing they can ask you is what we call the Torricelli principle or Torricelli theorem. Okay, the idea of Torricelli theorem is actually the theorem that suggests that when the water is exposed to an atmosphere, okay, so the flow velocity on the wave speed, okay, in Torricelli principle is V is equal to square root of 2gh. Okay, so but I'll come into that. So let's take one question or one or two questions in both continuity of equation and Bernoulli's equation. So for continuity of equation, right, there's a question I have in this place that I want us to solve. So I'll give out the parameters to us, right? Then we can find. So meanwhile, the applications of fluid mechanics like suction effect, like venturimeter. Venturimeter is actually an instrument or a device used to measure the flow velocity of a fluid. So, alright. So other applications of Bernoulli's equation, rather Bernoulli's equation, we have suction effect, we have aerofoil lift, we have filter pump, we have venturimeter, we have blood pressure measurement. The instrument we use in measuring pressure is called sphygmomanometer. Sphygmomanometer. Alright, so that's that. So let me take one question from this place or two questions. So the first question says that if the speed of a fluid in the pipe of cross-sectional area 100 centimeters square, so right, A1 is equal to 100 centimeters square, okay, then it's 30 meters per second. So you have V1 is equal to 30 meters per second. Alright, so what will be its speed? That means V2 is unknown, V2 is equal to unknown. Alright, what would be its speed? If the pipe is connected to the other end of the pipe, the radius of the second pipe is 10 centimeters. So R of the second pipe, that is R2 is equal to 10 centimeters. So this is what continuity of equation. So you can write solution applying continuity of equation, applying continuity of equation, right? So what do we have? Now your A1 is given to what? 100 centimeters square, right? So convert 100 centimeters square to meter square, all right, which is now 100. Your A1 from 100 centimeters square will now be A1 is equal to 100 divided by 100, then all raised to power 2, which is 100 over 10 over 100, that's 10 raised to power 4, because these two already, right? This 10 raised to power 2 raised to power another 2, that's 100 over 10 raised to power 4, which is 100 multiplied by 10 raised to power minus 4, then all into meters square. That is area 1. Area 1 has been converted from centimeters square to meters square. So V1 is 30, so you have A1 V1 is equal to what? A2 V2. So A1 is now what? 100 times 10 raised to power minus 4, then V1 is 30, okay? But they say you should look for what? For V2 unknown, but they did not give A2. So I said use what? A2 is equal to what? Pi r squared. They gave radius to be 10 centimeter. If it's diameter, use radius equal to diameter over 2. But if it's that means if it's diameter that is given, use A is equal to pi d squared over 4. But once it's radius, use pi r squared. So A2 will now be 22 over 7 multiplied by, so what is radius? 10 centimeters. So convert 10 centimeter to meter. That is 10 over 100, which is 0.1. So you now have what? Multiplied by what? 0.1 all raised to power 2. So that is A1, which is now 100 times 10 raised to power minus 4. V1, which is 30. V2 is unknown. A2 is now what? A2 is now the whole of the value you have from 3.142 multiplied by 0.1 squared. So input it as the value of A2. Make V2 solve the formula. V2 set the formula. So that is A1 V1 is equal to A2 V2. Then this over A2 and this over A2. So at the end you have A1 V1 over A2 is equal to what? V2. Or V2 is equal to what? A1 V1 over what? Over A2. A1 is 100 times 10 exponential minus 4. V1 is 30. And A2 is what? The whole of the value you have. So your answer is in meter per watt per second. That's in V2. So if you solve well, alright, your answer is 9.6 meter per second. V2 is equal to 9.6 meter per second. So solve that value and give us whatever you have. That is question number 1. Right. Okay, so that's question number 1. So V2 is equal to 9.6 meter per second. Alright, so that's that. Then the next question I want us to take, okay, before I give you a round of the class, is the question of Bernoulli's principle. Okay, don't forget that I've given the applications of I said sphygmomanometer. This thing I wrote on the board is the instrument we use in measuring the blood pressure, and the applications of Bernoulli's equation are suction effect, venturimeter, filter pump, okay, and blood pressure measurement, flow of liquid from tank too. Those are the applications of Bernoulli's equation. Application of Bernoulli's equation. Bernoulli's equation. So I said we have what? Number 1, we have suction effect. Suction effect. Okay, so you can check all of this. We have filter pump, right? So we have aerofoil lift, and we have number 4, venturimeter. Let me just use this. It allows us to do blood pressure measurement also. Blood pressure measurement. So the instrument we use in measuring blood pressure is what we call sphygmomanometer. Sphygmomanometer. Okay, the number 5 is 5 application is venturimeter. Venturimeter, I said, is a device, alright, used to measure the what? The flow rate of what? Of a fluid. Okay, so that is venturimeter. VENTURERIMETER. So that is that. Okay, so now let us look at the second question of Bernoulli's equation. The question goes thus: a long rubber hose, right? A long rubber hose of uniform cross section. Don't forget I said if it's a uniform cross section, your V is equal to 0. Alright, V is equal to 0 if it's a uniform cross section. Okay, so it's connected to a long rubber hose of uniform cross section is connected to water tap on the ground, full stop. To what height should the other end of the hose be raised so that the pressure drops by? So they give pressure to be 5 times 10 exponential 3 Pascal. If the pressure drops by 5 times 10 exponential 3 Pascal, so we are looking for to what height. So that means height 2 is equal to what? Unknown. So recall Bernoulli's equation, because if height is unknown, all right, and you are looking, you have pressure, definitely from P1, all right, P plus 1 over 2 rho V1 squared, all right, plus rho V squared plus rho GH. So by the time you find your P1, right, because I said changing what? Changing pressure, summary now is equal to what? Rho GH. Check that formula I proved initially. So what is pressure? Pressure is what? 5 times 10 exponential what? 3 Pascal is equal to. What is density? Density, because there isn't a water, all right, they said is connected to water tap. The density of water is constant. Water is 1000 what? Kilogram what? 1000 kilogram per meter cube. So you are going to have 5 times 10 exponential 3 is equal to, density is now 1000 multiplied by gravity is 9.8 multiplied by the change in height you are looking for. Alright, that's the height of the object. That's how to solve it. So you have 5 times 10 exponential 3 over what? 1000 multiplied by what? 9.81 is equal to what? The change in height. So change in height of the object is equal to, so that, what do you have? 5 times 10 exponential 3 over what? Over 1000 multiplied by what? 9.81. Your height at the end of the day should give you 0.51, no mistake, yeah, 0.51 meter. Okay, that is the total height of the what? Of the material. So that is that. Okay, so aside from this now, the other question they can ask you is Torricelli. So the equation of Torricelli theorem, alright, Torricelli is, so that is the protocol to follow. Just apply change in pressure is equal to, alright, rho GH, and find that. So from for Torricelli is total expression is to calculate, determine the waves, the flow speed. So and flow speed is V is equal to square root of 2GH. That is what we use to determine the flow speed. Then for venturimeter has like one equation that I'm going to give, or I'll give 3. If you are to calculate for pressure in venturimeter, this for Torricelli, from Torricelli theorem. You can study what Torricelli theorem is all about. Torricelli theorem, but that's the final expression to calculate the wave velocity. Alright, sorry, the flow. So the flow velocity, alright, so flow velocity is given, alright, from Torricelli principle to be V is equal to square root of 2GH. So this is the first equation of venturimeter. Venturimeter is an instrument used to determine the flow rate. This from Torricelli, flow rate of fluid. So you can use that first value if you are to determine pressure. Don't forget that change in pressure in venturimeter is density of the manometer, GH. Density of the manometer, GH. Okay, then the final value, alright, is when you have to determine the flow rate, the volume flow rate of what? Of a venturimeter. Use area 1, area 2, okay, then square root of 2 rho m. Rho m is density of the manometer, GH, over open bracket A1 square minus A2 square, then all into rho. Okay, all into the final density. So this venturimeter. So all of this can be used. Alright, so for Poiseuille's equation, you have V over T. So study Poiseuille's equation proportional to, I believe we have rho pi, we have rho pi over 8 VL. Alright, so Poiseuille's, let me just give you the expression of Poiseuille's equation. Then this R raised to power 4, so it's equal to R raised to power 4. Then the final value in that place is R raised to power 4. Then I think we have eta. Okay, so Poiseuille's equation is given as pi over 8 eta L, rather eta L, because of viscosity L. Alright, then R raised to P, R raised to power 4. Yeah, this Poiseuille's equation. Poiseuille's. Okay, Poiseuille's, LLES, Poiseuille's equation. Okay, that's this Poiseuille's equation. So your P is rho GH. So impute rho GH in that place. So use that expression to determine Poiseuille's equation. So this one is for all right, ventimeter equation. So you can use any of these. This first one in ventimeter is to calculate for pressure, second one is to calculate for the volume fluid of the liquid. All right, so that is all I can say for now, all right, on fluid mechanics. Okay, so please do well to go through all of the things you have done, right, and God bless you. Okay, see you in the next video. By God's grace, take care.